Hello, welcome. So as you already have seen the intro, I was on the countryside at that time in my Easter holiday and I recorded that short intro. My name is Balosin. I came from Austria, from Wien. I worked there as a software architect. Besides the software architecture, which I do on daily basis, I'm actually an independent technical trainer. I conduct courses on the software performance, software architecture and Java tuning and performance topics. I also write mainly for InfoQ and everything is also on my website, jonasbalosin.com. I'm more focused on the performance and tuning topics, but also software architecture, mainly agnostic of technology. And I'm also speaking to a lot of conferences. As you can see there, I attended a lot, so a lot are still upcoming on my agenda. What's the content for today? The talk is called Demystifying Java Language Features from 9 to 11. In my assumption, to demystify means to reveal how it is implemented under the hood, because based on those implementation patterns, you can learn a lot. You can reuse them in your daily basis applications. So the content actually has few topics. Most of them are part of the JDK 9. If you see this timeline, in JDK 9 there were really a lot of language features, I would say. JDK 10, JDK 11 less, but more under the hood. They enhance the compiler, they edit new garbage collectors and so on. So basically today I will go through each of these topics and explain you a bit how they work under the hood and how to use them properly. And as I was saying, it's a good lesson learned from you to steal some out of these implementations and you apply them on your daily projects. First of all, it's about private interface methods. This was part of JEP. It's called JEP 213. And this JEP, it's in regards to the project coin. Project coin, it's actually the project itself adds small features to the language. And across those small features are these private interface methods. How you can use them, actually, very simple. You have the interface, and in that interface, you can have a default method, and the default method actually calls the print, which is a private void method, which does something very trivial. And how it works under the hood, how the Oracle engineers ended up with such, because before this we didn't have the support for private interface methods. Bottom it's actually the bytecode. So and the top it's the code that it's written by the developer. By the way, I forgot to mention everything I posted on my channel, on my website, so there is no need to take pictures. I will give you the link and you can download the full presentation from there in the PDF format. So how it works, actually, the foo method, it's just a normal method, and it does an invoke interface call, which is actually a call which says, hey, dispatch this call to a method which belongs to an interface, and that method is our private interface method, which is the lowest one, private void foo, and there is the bytecode sequence. So in essence, there is nothing particular, nothing specific to this mechanism of adding and handling these private interface methods. They are just called like any other interface method. And as you can see, actually the default void foo method contains the default, but at the bytecode level here down there is no default keyword. So it is only syntactic sugar. It doesn't exist at the bytecode level. Next one, it's about static private interface methods. It's actually the same principle. You have a method which is a buzz method, which calls another one. It calls the static print this time, which is a static private interface method, which just prints something. And under the hood, how it is compiled and how it works, it's the same principle. The private static method, it's the lowest one. It doesn't contain anything specific. It's like any other private static method you declare in all other places, and it is called from buzz, it is called via an invoke static. Invoke static is actually the bytecode op which is used at the bytecode level to call any other static method. So roughly speaking, there is no specific mechanism to deal with these private interface methods, neither for static one nor for the non-statics. Maybe the next, it's a bit of interesting because it's about strings. The internal string representation in JDK 9 was actually improved. And let's start with JEP 254, which it's actually in regards to compacting the strings. What it means, before JDK 9 until 8 inclusively, all of those strings, so every time you declare a string, it was backed by a char array. And if you profile or if you had profiled your applications, most of the heap was actually consumed by strings. And in your application, you can have thousands, 10 of thousands of such strings, and they consume a lot of heap. On top of that, most of those strings could be backed or could be are late in one characters. And why not? Let's compress them in order to save the memory footprint. And this is what they did. They changed the char array into a byte array because if it is late in one, it could fit 1 byte. And on top of that, there is the coder itself. The coder is actually a switch between the Latin 1 encoding scheme and UTF-16 encoding scheme. By default, it goes and tries to compress it to make it Latin 1 because it saves the space, it preserves the memory footprint, and if it fails, it switches and falls back to the UTF-16, which is actually analogous to what we had before. One character takes 2 bytes. This is a graphical implementation of how it looks like. We have a very simple example, the string Java C. How it looks like with the UTF-16 encoding, you can see each character JAVAC, right, takes 2 bytes. However, for each of these, the upper byte it's 0 because it's a Latin 1. So it could be easily stored using the UTF-16 with the scheme below. And of course, you reduce the amount of space. Here it's a screenshot from Eclipse Memory Analyzer. I try to provide you a clue about a measurement, how much space you, for example, save. In case of UTF-16, the retain heap, it's 56. It's actually outlined there, top right. Retain heap, it's actually the heap which is freed when you, for example, remove an object. And the shallow heap is the size of the instance itself. The retain, it's always bigger because it could store other references. So implicitly, you remove everything if there are no other pointers. And in the Latin one, it's 58, so it's a bit lower. However, this is just a synthetic example. In your real case application, when you have a lot of strings, the difference it might make a difference. And the thing is, if you have only one character in your string representation which couldn't be stored as a Latin one, in this example it's the last C, it falls back and uses the UTF-16 encoding scheme. And of course, it's actually, you consume the same amount of space that it was before with the char array. An interesting example is how the string is constructed under the hood. This is a method from the JDK, from Java string, from Java string.java source class, and you can see here, by default, the compact scheme is enabled. So every time when you try to create a string, it tries to compress it because the compacting scheme is enabled by default. It's the one marked with 1, and if it fails, which means there is at least one character, which is UTF-16 character, it falls back and uses UTF-16. But by default, it tries to compress because it's obvious that it tries to save the space. And having this rationale in mind, what I've created a test. This benchmark annotation, are you using GMH? Who is using GMH? Okay, not really a lot of people. GMH is actually a nice tool if you want to do micro benchmark testing. In my opinion, it's the way to go to use GMH. So that annotation belongs to the GMH. It's part of the JDK, by the way. It was included, so you just have to use it. So what it does actually, it creates this. First, I've declared 6 strings. Each of those you can see are UTF-16, and then I try to have a measurement around the concatenation of those strings. So how much time I consume to concatenate all of these 16 strings with the compact strings scheme enabled by default, because the compact string, it's enabled by default when you start the JVM. And as you can see here, I measured the allocation rate and the average time. Average time, of course, if it is lower, it's better. And you can see it spotted there with by disabling the compact string. So by disabling the implicit option from the JVM, I've got a better performance. And now you can make an analogy why, right? Because first it tries to compress the string and it fails because all the strings were UTF-16. However, if I disable this, it doesn't try to do that anymore. So it's quicker. And in terms of allocation rate, it's the same because they are the same strings. And this is the first takeaway. If it is suitable for your application, think of disabling compact strings. Because if when you create the strings and when you do operation with the strings, if they are UTF-16 or the majority are UTF-16, try this trick. Maybe it helps and improve a bit of the overall performance in your application. Another thing is how the strings are actually compared to decide if they are equal or not. And this is another method from the JDK, is the equals, which actually, as you can see, it's highlighted if the strings have a different coder, right? The comparison returns false because it doesn't make sense anymore to go to compare all the bytes. However, if the coder is the same, it traverses the byte array and decide if they are really equal or not. And here it let me, this rationale let me to create another benchmark. This time I took two strings, two sets of strings. The first two are identical and they are Latin1 strings, and the second two, the third and the fourth, are UTF-16. And what I did in this test, I created 3 benchmark scenarios. The first one, which compares Latin1 to Latin1 strings. The second compares Latin1 against UTF-16, and the last one UTF-16 against UTF-16, because I was curious about the performance. And what are the results I've got with the compact strings enabled by default and without compact strings enabled by default? The noticeable case was when you compare strings which have a different representation. So if you compare strings which are Latin1 against UTF-16, the performance is better because they just check if the coder is different. And of course the coder is different, so they really don't touch the byte array. However, for all the other cases, for example, with compact strings, comparing Latin1 to Latin1, it's a bit faster than comparing UTF-16 to UTF-16 because there are less bytes in that array. On the right side, for the compact strings with the compact string disabled, the performance is almost there. So it is analogous to the previous JDK implementation. Next thing, which was actually, it's quite important, was in regards to indify string concatenations. Let's take this example. Let's suppose you have to concatenate a string plus an integer plus a float, right? Before JDK 9, how it was? If you zoom inside, even if you, for example, do even if you use the plus operator, right? They are not created strings. However, it's using string builder. So this is a sort of optimization to preserve the number of strings created. And as you can see here, the string builder is initialized, and then it's appended. All of these are appended, and then the toString gets called on it. However, this brings to some rigidity because, and it's not extensible for further optimizations. So this is a JDK8 or Java 8 bytecode. However, starting JDK9, they decided to remove this string builder sequence, which is generated when you run javac, when you create the bytecode, and how it looks starting JDK9, of course, including 11. It's based on InvokeDynamic. In InvokeDynamic says roughly don't do it at compile time, let's do it during the runtime. And this concatenation, it's actually handled during the runtime, implicitly not anymore by creating string builder objects, based on some strategies. So this InvokeDynamic actually uses under the hood during the runtime few strategies to concatenate the strings. And here it's a JVM flag. You can choose your strategy if you want one which is not default by that option in there. And currently, there are 6 such strategies. Just to quickly go through them, 2 categories. The first category, it's still in regards to generating of that string builder append sequence. But this is not generated anymore using javac, but is generated during the runtime. So the first 3 things ends up with the same string builder append sequence. However, it is generated during the runtime and not upfront. And there are slightly flavors between them. The first one is actually analogous to the JDK8. The second one, SB sized, what it means, it tries to guess the size of the string builder. Why is that? Because if you don't guess the size of the string builder gets resized. So getting resized all the time, it means extra allocation and extra copying, and of course this impacts as well performance. But this is not precise enough, because if you have arguments, you cannot guess the accurate length for those arguments. And the third one, it's actually what it does, it creates the string, measures the length, and calls the string builder with a precise size, so avoiding any resizing during the runtime. And the last 3 categories, it's actually using a method handle. This method handle, it calls the string builder during the runtime. And the same, first one tries to guess the size, the second one tries to create the string, takes the length, and then calls via method handler, calls the string builder. And the last one actually doesn't use any more string builder. So the last one, it's actually the default one in our JVM. When you start and you try to concatenate, it uses the last one, and it doesn't use anymore, as I was saying, string builder, but uses only a char array representation. So implicitly, it should be faster. The problem with this is it relies on some internal API, so it doesn't rely on the public API. And with each upgrade of the JDK, there might be, I mean, they need to take care of this as well, because it uses some internals, but on the other side, it's the one that offers better performance. In terms of timings, I've did some tests. Actually, I measured JDK GRE, actually 1.8, the first row, using each strategy from the GRE 11.0.10. And as you can see, the top one was the slowest one, and actually it's good, because otherwise, if the top one would have been the quickest one, it would have been a problem. So actually, the strategies added for this added a bit of improvement. In essence, the last one, which is the default one, was the fastest one, also in terms of allocation rate, around 200 bytes per operation, and also in terms of average time. As you can see, the one in the middle was somehow comparable, and the one in the middle, what it does, it first creates the string, takes the length, and then uses the string builder with the append chain of sequence with that specific length, so it avoids actually the resizing. And this is another a bit of advanced trick. In this particular case, the one in the middle and the last one were more or less of the same performance, because just-in-time compiler during the runtime was able to optimize all the append chain calls. And that's why at the end the performance was similar to the last one. However, you might face situation which if the just-in-time compiler is not able to optimize this append chain of sequence, probably the last one, which uses the direct char array representation, will be quicker. That's why it is also enabled by default. And these are the conclusions I already talked about. This strategy of delaying to the runtime brings a bit of improvements, and also there is no sense to recompile your bytecode if you migrate from one version to another for Java, because you benefit of this during the runtime. So your bytecode should stay at least in theory in the same shape. Stack Walking API. This is quite an interesting API. It's part of JEP 259. It's actually a way to traverse the stack frames in a lazy way, which means you request a frame only when you need it. You can limit the stack depth, so it means you cannot traverse all of them, and you can filter the frames. So it's very, very streamway oriented. And you might have wondered what was the issue with the previous, because also without this API you can get the stack frames. Yes, of course, but the problem with the previous or the older API was when you call get, for example, stack trace, you get the full stack trace elements for the full stack. Even if you are interested in only 2 or 3 of those, right? Everything gets created, and its performance from performance perspective, it costs you a lot. This is actually the API, how you can use it. It has a get instance. You can use get instance with few options. By default, you cannot get, for example, the hidden frames. For example, those hidden frames, every time you create a lambda, you have such hidden frames. So by default, you cannot see them, and also some reflection frames. You can play with these options based on your case. And the last one has the last parameter, estimate depth. So actually, if you are not interested in the full stack trace depth, you can say you can bound to a specific size. And just to give you a matter of, for example, performance-wise characteristics, how much it costs to just take the current stack frame. For example, you have a method which recursively it's called by itself until it reaches a depth, and then you stop there and let's take just the top stack frame. Here is the code, how it is measured. So you have the method. The method itself, it's calling the recursive method. The first method is the benchmark method, which is getting measured. This one calls a recursive method. When the recursive method reaches the threshold, which means depth is 0, it calls the last one, and here is the Stack Walker API. You say get instance, you walk through the stack frames, get the first one, and that's it. It's very simple and very API streaming oriented. In terms of performance, as you can see, the Stack Walker API was always faster, and it was constant around 1 to 3 nanoseconds, independent of the stack depth. And this is very, very important. In the classical approach, the get stack trace, you can see bigger the depth is, slower it is, because you pay the cost of, for example, filling in plus creating all the stack trace elements. So it's much more efficient if you have to profile these stack frames to use this API. However, I would give you a trick. You can even speed up more on this. For example, if you process asynchronously the throwable frames. What it means? In the classical approach of using this, for example, Stack Walker API, everything is synchronously to the caller thread, right? So you cannot process it asynchronously. And you might have cases where you, for example, want to inspect and trigger some errors for some monitoring tools, right? This would be a business case. And And if this case it's your application, it's always better to do like this. So the thread which actually holds creates the trouble in one thread and then dispatch it to another thread. So in this case, the first thread pays only the cost of filling in the stack trace and not all the cost. So you just create the trouble, dispatch it to another thread, and in the second thread you do the heavy work. Versus in the Stackwalker API, for example, you have to synchronously process in that thread. There is no other way. And in this case, for example, just to traverse backwards the frame, so you stop on the current stack frame and you traverse backwards and stack frames, you can see the comparison between the stack walker and just creating the new trouble. And it was always faster just to create the new trouble, because as I was saying, you can afford processing the trouble frames in a different asynchronously thread, and it's way faster. And this is actually another trick. You can take it and apply it in your application if it makes sense or not. SpinWeight hints. This was another one added in JDK 9. What it does actually, the API is thread.on SpinWeight. And what it tells, it actually imagine you are in the busy waiting loop, waiting for some events to happen. But those events to be suitable for this on SpinWeight API, these events should happen very quickly, should be shorter, and should have a higher rate. And this is a perfect case to use on SpinWeight. It's actually, if you want a producer-consumer paradigm, when you have a lot of items produced, and the consumers, it's asking, am I ready to consume? No. If it is not ready to consume, it still does a bit of busy waiting until there is something ready to produce. And why is such a good option? Because actually this on SpinWeight method, it uses some instructions which are supported by, for example, in this case, x86 hardware, which are actually like NOOP instructions. So basically it tells the CPU, I don't want to be descheduled to end up in a context switching, which is costly. I don't give up of my time slice, but keep me busy, keep me looping a while. In this case, it also reduces the pipeline instructions, so it implicitly saves the power. So it's very useful API, but again, it's limited to only a part of the problems. And here it's a comparison between on SpinWeight, yield, park, nanos, and sleep. And as you can see, sleep is the worst one. You can also say I'm going to sleep one millisecond. But actually the sleep, it's the worst one because sleep does always the context switching. So you end up in the context switch and then you need to be rescheduled again. And also you can see the context switches for sleep. It's like 9 times bigger than all the others. You can also say yield. Yield doesn't guarantee you that you release and the OS scheduler prioritize another thread. However, you are at the mercy of the OS scheduler to do that. So that's why on SpinWeight, it's a way to go further in this kind of paradigm. However, be very careful because on some architectures, if you are using Spark, it's not there. So it's there for x86, but for other platforms on Spark, for example, it's not the case. Collection factory methods. This is an API actually added still in 9 to create compact and unmodifiable collection interfaces. So in one line of code, you can create these compact and unmodifiable connections. And this is the API list of, set of, map of, or map of entries. And what is so magic around it? If you can zoom inside the JDK implementation, you can see list of has a lot of declarations for different set of parameters, right? And if you have to count them until 10 arguments, there are dedicated methods, different signatures. And starting with the 11th one, there is a vararg method. If you would have to write such code, right, would you do in this way? Yes, why? For? Yeah, so actually, yes, exactly. That's the trick, especially if you write libraries, right? If you write libraries, you want performance. So varargs, it's very, very inefficient way. And here, this is a bit of assembly just to prove you what it does under the hood. Every time you call a method which is a vararg method, it's exactly like you said. It allocates an array. It copies all the elements in that array and calls the method because in from and under the hood there is no vararg, right? So everything it's handled within an array. So you pay off this additional cost of allocating and copying elements. So that's why the JDK guys implemented this tree, because probably until 10 it's a reasonable threshold for the most use cases. So you don't pay the cost of the vararg, and this is the probably something that you should reflect on it. Just to give you an idea, when you call explicit versus vararg with different number of arguments, you can see the timings are way better when you do explicit versus vararg. The second takeaway out of this implementation, if you zoom inside the wrappers, how those objects are stored, for example, you can see for one or two elements there is a dedicated wrapper. It's which actually stores those two elements. And starting with the third number, for example, if you say list of A, B, C, it's the last one, which has list N as a wrapper. And how is it going under the hood in the implementation itself? It's actually list 1, 2, they are just E0 and E1. And starting with the third, it's an array of elements. If you may question yourself, why is that? Would you guess why? Why is better to have packed elements and not arrays? That's actually the general question. Yeah, exactly. That's the point. Actually, every time you can create, when you create arrays, you have an additional level of indirection. That's the problem. So, and if you don't traverse the array in a predictable way, even the hardware prefetcher cannot get you any benefit. So that's why this is actually the layout of creating an array of elements versus creating packed elements. When you create packed elements, if you, for example, have E0. If E1 is small enough, you have a very high chances to get it in the CPU cache line, because it falls on the same operating system page. Both are coming together. So that's why they decided maybe to implement this trick, because probably list 1 or 2 is the majority of cases, and let's try to make it even more optimal. In nutshell, reduce memory footprint and data locality. I think this is, at least for me, it's a very good lesson learned how to deal with these optimizations if you are in the position to write such libraries. And set off and map off are implemented based on the same rationale, nothing particular. Local variable type inference. This is now switching to JDK 10. Actually, it's very simple. You can use the var, and you can say var. You can define using the var, and what happens under the hood, Java C, when you try to compile, Java C actually based on the value itself, if the value has sufficient information about the type, it actually creates the real type. So it's only, if you want, sugar, syntax sugar. There is no concept of dynamic type inference. It's only static type inference, because Java C does this translation. And here on the top, on the bottom, sorry, you can see all the type it's implicitly inferred to the right one. However, there are cases when this might not be true. For example, in case where you have, for example, bytes, short and longs, and you don't provide a specific hint, they are automatically either widened or narrowed to integer. So be very careful. You need to provide hints for the Java C. So when the bytecode is created, the appropriate type needs to be chosen. And here it's actually what I was saying. When you have a numeric value, especially for integer literals, you might be surprised or not, because they might be widened or narrowed to the integer implicitly, and you might, for example, lose some numbers. The second thing is when you call, for example, generic methods, when you use the diamond operator, sorry, if there is no target type to deduce the real type, or neither the constructor or the argument method tells you that, again, it falls back to object. This might be a trap in some cases, so be careful with this. However, these were a bit of telling stories. What is really important about this, and this is actually some things that were not possible before, it's about non-denotable types. What is a non-denotable type? Everything which is generated by the compiler, it's called a non-denotable type. And these non-denotable types, you cannot write them out in your Java source code, because they are generated and you cannot refer at the source code level. And there are a few cases, like for example, anonymous types, like intersection type across multiple interfaces, capture variable types. So all of these are generated automatically. And if you take this example, you have this object which actually defines the method foo. It's actually an anonymous class. What the compiler generates for you, it generates something with $1 at the end. So this is like another .class file which contains this implementation. And if you want to call object.foo with var, it's possible. Without var, it's not possible. So here I said var object equals, and here I say object foo. Why? Because implicitly the type it's inferred. If you don't use var, this call it's not possible, because you cannot say I want this, the object it's non-denotable type $1, and I want based on this to call foo method. So this is actually a very nice addition to the language. I would say, in my opinion, probably the best one. The other ones, you should be very careful with them, when to use var, because it's not always good. However, this is a real enable of the language. The last one is about nest-based access control. It's quite short. In essence, what it says, you have an outer class and an inner class. And the inner class has a reference to some private, could be a method or could be a field, which belongs to the outer. In our case, the inner class has a method foo, which calls the private method foo, which belongs to the outer. How was before Java 11? Actually, because every class, it's a top-level class. It compiles in a different class file. Of course, you cannot refer from some private which belongs to the other. And that's why they added some access bridge methods. And in this access bridge method, it calls the private method. So this is a trick, actually, to leverage this private access from another class. However, this has some drawbacks, so it's not so nice, right? So it subverts encapsulation, it increases the code size because of those access methods, can confuse some tools, right? Because they have, in addition, some methods generated, which are called bridge methods, and it's another layer of indirection. Performance-wise, it's not really a constraint, because just-in-time compiler can optimize it. And what they decided to do is to remove this mechanism, and they added the concept of nests. What is a nest? Nest is actually an entity which has access to another entity, even if that entity has some private stuff in it, without being necessary to add these bridge methods. And how it looks like, actually, you can see this is the generated version of it. You can see in this case, the method inner calls directly the private method, which belongs to another class, without being necessary to generate anymore the access class. So no bridge method anymore. That was all. Thanks a lot. If you want to download the slides, this is the place, my website /talks. I will put there everything. You can also read my blog post. I'm more focused on performance and these kind of things. As a further readings, there are the last two in addition. Thanks a lot.